So the functions phi naught and phi 1 have a very specific structure. So these are polynomials due to the quantization of energy and due to the boundedness of our wave function. So these polynomials are known in mathematics as the Hermit polynomials or Hermit functions. So, and they are denoted by Hn of x. Now, if we fix the coefficient of the highest power of the Hermit polynomial, so the Hermit polynomial n will have a highest power of x to the power n, and if we demand that the coefficient be 2 to the power n, then that fixes all the Hermit polynomials, the normalization of a0 and a1, and we get that h of 0 is then 1, and that h of 1 is then 2 of x, and h of 2 is 4x squared minus 2. H of 3 of x is 8x cubed minus 12 of x, etc. See that the Hermit polynomials are either even functions or they are odd functions. Then the wave function of our system is going to be given by the nth energy level wave function will be given by some normalization constant we are going to call Cn, and then the Hermit polynomial Hn of x. But of course, if it were just the Hermit polynomials, this wave function would not be normalizable, because as we go off to infinity, this polynomial will diverge because its highest power will dominate. So we multiply it by e to the power minus x squared by 2. Remember that we had said that this is going to be phi of x. So this is basically the structure of our wave function. So these there's a lot of mathematical literature dedicated to the Hermit polynomials. Let us just review a few of them here. So what is a Hermit differential equation? Well, we have seen this before, but let's write it in terms of h. So the h double prime minus 2x hn single prime plus 2n, where n is an integer, times hn is equals to 0. So n is a positive integer. So it can be 0 or 1, 2, 3, something like that. Also called the natural numbers, I think. So the Hermit polynomials are the solutions to this differential equation. Now, the Hermit polynomials they form a complete basis of function for functions defined on any Hilbert space. Just as e to the power I kx are a complete set of functions that we can use to express any function in a Hilbert space. If you have a function of x, we can express this as, say, 2 pi h bar square root e to the power minus I kx. Sorry, e to the power minus I px over h bar a to the power p d of p. So, just as is a Fourier integral, we can express any function on a Hilbert space as a Fourier integral. We can express any function on the Hilbert space as a sum of some coefficient times Hermite. So they are equally good as the basis of a Hilbert space. However, this is an aspect we won't be exploring in this course. The Hermit polynomials also satisfy some very nice recurrence relationship, and these are not very hard to show. So for example, the first one is the derivative of the Hermite is given by hn is given by 2n times hn plus 1. And then number 2 is hn plus 1 minus, say, 2x hn plus 2n n minus 1 is 0. And then we have number 3, which is hn plus 1 is equal to 2x hn minus h prime of n. So if I know h of n, of course, I can take its derivative, and that'll give me h prime of n. Then this recursion relationship then will give me h n plus 1. So if we know one Hermit, we can figure out all the others. So this leads to a very nifty idea, the idea of the generating function. Wouldn't it be nice to have a function which in some sense, captured all the Hermit polynomials? So a function that contained in it somehow all the Hermit polynomials. So this is the idea behind a generating function. So suppose that there is a function, we're going to call it g of x, and it'll also be a function of an auxiliary variable, which we are going to call small h. And this will be a power series in h, so it'll have terms which are like h to the power n divided by factorial of n, and then we have sum over n, where n goes from 0 to infinity. And the coefficient of each term is going to be the Hermit polynomial n, h of n. So this is what we call a generating function. And the nice thing about it is that if you could find such a function, then if we took the nth derivative of this function with respect to, say, h, and then set h equals to 0, then that would give us automatically hn. So how do you find this function? To find this function, let's just take the derivative of g, and then once you take with respect to h, now once you take the derivative of g, it's not very difficult to show using these recursion relationships that g satisfies this particular differential equation. So we can integrate this differential equation, and then we can get g, which is x, g of x and h is going to be some factor which is quote-unquote constant. It can depend on x because we are integrating this equation with respect to h, so the integration constant can still depend on x, and then e to the power 2x of h minus h squared. So this is the required function. Now, we can use the boundary condition where when g of x of 0 is c of x, because if you put h equals to 0, this just becomes 1. And according to the definition of g of x, if you put h equals to 0, all of these guys all of these guys will go to 0 except the one where n is 0. So that should give us h0. So this should be equal to h0 of x. But that is something we decided to be 1. So if I do this, then of course it fixes this normalization, which turns out to be a real constant, not a function of x. Then g of x of h is going to be e to the power 2 of x h minus h squared. And therefore, the nth Hermit polynomial will be given by the nth derivative with respect to h of e to the power 2xh minus h squared with h set to 0. Now, with a bit of mathematical manipulation, you can show that this can be rewritten in the following form. This is minus 1 to the power n e to the power x squared. I think this should be, yeah, that's fine, e to the power x squared. And the derivative with respect to x, e to the power minus x squared. So this simple formula gives you any Hermit polynomial that you want. Now it can also be shown that the normalization factor is up to some phase is given by 2 to the power n factorial of n square root of pi then square root, so that our wave function psi of n is given by 2 to the power n factorial n square root of pi e to the power minus x squared by 2 times hn of x. So these wave functions satisfy the normalization, orthonormalization condition as psi star m psi n d of x, where we integrate from minus infinity to plus infinity, and that will be given by the Kronecker delta of mn. Now another thing to discuss is that because this is an even function and the Hermits are either even or odd functions, so if a Hermit is odd, then psi of n is odd. If the Hermit is even, this is even. Of course, this is a result of something that we discussed in a previous lecture when we showed that if we have a potential which is symmetric, then its wave functions are either even or odd. They have very definite parities. And here we see that the even Hermit are even functions and these are odd functions for n odd. So let's sketch the first few Hermit functions. So psi of 0, is going to be some constant, right? So we know that in the first case, this is just a constant, so this will be just a Gaussian. So we expect this to look something like this. And then the psi of 1 is going to have a straight line times a Gaussian. So, and the straight line will go through the origin. Sorry. So as a result, the wave function should look like this. Sorry, my drawing is not very good, but of course it also agrees with what we discussed about the general features of bounded wave functions, where if we have nth energy eigenstate, then it should have in total n plus 2 zeros. And if n was 0, then it would be the ground state, then the 2 zeros of the wave function would be at plus infinity and minus infinity. For the first excited state, we see that there's a 0 at the center, and then there will be 0 at the positive infinity and 1 at negative infinity. So similarly, if I look at psi 2, psi 2 will be some kind of a parabola, and but because of the it's multiplied by a Gaussian factor, it'll be given by something like this. So this is even, and then psi 3 will be odd. Similarly, so there'll be more bumps or more nodes like this, so on and so forth.